Welcome to Pomodoro Joe for Thursday, February 2nd, 2023. Today we're doing LeetCode problem 953, verifying an alien dictionary. This is an easy problem. And the problem statement says, in an alien language, surprisingly, they also use English lowercase letters, but possibly in a different order. The order of the alphabet is some permutation of lowercase letters. Given a sequence of words written in the alien language, and the order of the alphabet, return true if and only if the given words are sorted lexicographically in the alien language. And then they give some examples. So this is essentially just saying we have some alien language, it uses the same characters as English, but their alphabetical order is different than our alphabetical order. So we just need to say whether or not this list of words that they give us is in their alphabetical order. All right, this should be a fun one. So with that, we will put 25 minutes on the Pomodoro timer and get started. So the first thing I am going to do here is create some mapping to hold on to our order. And I'm going to use a dictionary for that. A dictionary is a great way to do a key value store. So you can give some character as the key and it will return the index or of the order as its value. So we will have a character map. All right, and now we will fill that map using the order that they give us. So I'm using enumerate here, so it will return the index and the character in this string. And then all we need to do is set our character map key as the character and the value is the index. All right, now we've got our character map set up. So the next thing we want to do is create a function that will take two words and return whether or not they're in lexicographically sorted order. So for that, I'm going to create a new function and call it comparator. So a comparator is something that you will find in many languages. So the comparator will take in two values and essentially return an indicator of whether or not they're sorted ascending, descending, or if they're in the same order. So for us, I'll take in A and B, and I will just define our return values. We'll say -1 is ascending, 0 means they're the same, and +1 will mean they're descending. It doesn't really matter. I could have chosen these in 1, 0, -1. All that really matters is that we agree on the meaning. Okay, so the first thing I'm going to do is actually just short circuit this if I can. So if A is equal to B, we'll just return 0. They're the same. Okay, so the next step is to go through every character in A and B, checking for ascending, same, or descending. Now, what happens if A and B are different lengths? Well, we'll try to take care of that here by finding the shorter of the two and then just comparing all the characters up to the end of that word. Now with our min count, we can say for some index in range 0 to min count, 0 is implied. Now we can do our comparison. So to make this a little bit easier, I'll actually define the index of the character at A, and we'll get that by looking the character up in our map. So we'll look in the character map, and we're looking for the index, or the lexicographical value, I should say, of the character in word A at index I. We'll do the same thing to get the lexicographical order for the letter at index I in word B. Now that we have the two orders of these characters, we can do the comparison. Okay, so we have two comparisons so far. If the character at index I for word A is less than the character at index I for word B, then these are in ascending order. And conversely, if the character at index I for word A is greater than the character at index I for word B, these are in descending order. Now, if they're the same, we need to keep checking. We can't just return. Now, if we make it through every single character in our words, and they've been the same so far, we've only checked the minimum length word. We haven't checked the entire length of both words. So now we have to check if there are additional characters in each word. If A has more characters, then A is actually later in the dictionary, or later lexicographically, than B. So if A has more characters than B, then A actually comes later in our dictionary than B does, which means that we have to return descending. Now, if length of A is less than length of B, then A does come before B, so this would be ascending. And now if they're both the same length and the same set of characters, then this is going to be the same. We probably will never get here because we check for the sameness up here. Okay, now we have our comparison that takes two words and will tell us whether or not they're ascending, the same, or descending. Now we get to the final part of our problem, which is to go through every single word in our words list, checking to see if they're in ascending order. Okay, so now we just need to go through all the words in our words list and check to see if they are in ascending order. So for this, I'll say for some index I in range, and we'll start at 1 and go to the length of our words list. Now we're starting at 1 so that we can check the first word against the previous word. So we can just say if, let me grab my comparator here. So if we take the comparator of our words at, we're going to say I minus 1. So this is the previous word. And we check it against our words at I, which is our current word. If that ever equals descending, which is 1 in our definition up here, if that ever equals descending, then we need to return false. This is not in lexicographical order. If it's the same or ascending, then we're all fine and we can return true at the end. All right, I think that is basically it. We've got our character map that gives us the ordering. So when we give it a character, it returns the lexicographical order of that character. We have our comparator that checks word A against word B. And we have our loop that goes through every single word, checking it against the previous word to see if it's in ascending order. All right, let's give this a run. All right, that seemed to work. Let's submit this and see how well we do. And we pass. Not too bad. We beat 69% for runtime and 77% for memory. So that's pretty good. Now there's one optimization I do want to try just because it's something that bugs me. One thing you'll notice in our comparator here, we're grabbing the length of A and B, and then we do it again down here and again here. We're grabbing that length 3 times for each A and B. That could be reduced to 1 check. So we'll do length of A is equal to length A, and length of B All right, and then I'll just replace all these function calls with these variables. All right, now that I've replaced all those function calls with variables, that should actually save us a little bit. I know it seems like a minor change, but little changes like that, especially when you call comparator many, many times, can actually add up to make quite a difference. Make sure we still got everything running, and now we'll submit that. Bam! Look at that. Just by changing our algorithm to use cache lengths for A and B, we jumped to beating 93.63% of other algorithms for runtime. That's up from 69%. That's pretty darn good with little impact to our memory footprint. All right, I totally encourage you to check this one out. This is super fun. It's an easy problem, 953. Check it out on LeetCode, and you can check out my code on GitHub. The links are in the description. Hope you enjoyed this. Hope you had fun. Hope you learned something. And remember to please always endeavor to write better code. Better than me, that is.